So today we are going to talk about the Favorskii rearrangement. This is one of the important rearrangement reaction, molecular rearrangement. So frequently questions will ask from this Favorskii rearrangement. So in the Favorskii rearrangement, we have a alpha halo ketones converts into esters. So when we have a alkoxide ion here, okay, here halo means not all the halogens, only chlorine and bromine. Fluorine and iodine we will not see the Favorskii rearrangement, only for the chlorine and bromine we will see Favorskii rearrangement. And now here also we can use, instead of alkoxy, if we use hydroxy ion, then the product what we will get is carboxylic acid. And when we use amide, sorry, NH2 minus, so we'll get amide. Okay, but Favorskii rearrangement means conversion of alpha halo ketones into esters. This is called Favorskii rearrangement. And then we'll go for the mechanism here, and we'll see. So this is the alpha halo ketone. We have a base here, so base will abstract hydrogen from here, not this hydrogen, because so here this reaction goes through the formation of three-membered ring. So if it abstract proton from here, it will not form three-membered ring, and also it follows SN2 mechanism. So SN2 mechanism means like leaving group goes from here, and this negative charge, after abstracting base, this negative charge comes and attached to this. We'll see in the mechanism. In the first step, it abstracts this proton, base abstract that proton, and here we have a negative charge and chlorine, and here we can say SN2 mechanism. So this is the one of the intermediate. Okay, so now we know that the stability order of these cyclopropanone we have, and cyclobutanone we have, and cyclopentanone we have, and cyclohexanone also we have. So which is more stable? And this is the more stable, because here angle strain is less, whereas here angle strain is more. Because of that, this is less stable, and less stable means more reactive. So because of that reason, this immediately undergoes reaction, so it has to open the ring, otherwise it cannot be more stable. Now alkoxide goes and attacks to this carbon, this will be O minus and OR, and this bond comes like this, this bond open like this. Now COR and negative charge, and further H plus goes here, so we get this product. And here in the Favorskii rearrangement, ring contraction takes place. We can see in the starting product we have a 6-member ring, and final product we have a 5-member ring. And there are another mechanism we have. This is the actual mechanism for Favorskii rearrangement, and there also we have concerted mechanism. So the concerted mechanism, later this is not acceptable, because in the concerted mechanism, if you draw the same, like we will take same only this alpha halo ketones. When we go for the concerted mechanism, here this comes here, so everything will happen in a single step. and here there may be chances for formation of a mixture of product. So imagine that I just uh, this carbon I just labeled as a star. So this is the one product what we will get here. The another product will be this one, but actually in a Favorskii rearrangement only we will get only one product, but here we are getting mixture of products. So in the concerted mechanism, here we can see we are breaking this CC bond, and we are making this CC new bond, and also we are breaking CO bond, and we are breaking this CCl bond also. Everything is happening in a single step. That's why we call this a concerted mechanism. So but that this concerted mechanism is ruled out because in Favorskii rearrangement we will get only one product, whereas in concerted mechanism we are getting two products. Okay, so because of that this mechanism is acceptable compared to this. Then this is for the cyclic compounds, and we will see the mechanism for acyclic compounds. pH, CO, CH2, this is CH2 and Cl here. And now we'll see the mechanism for this. Here also we have OR minus, that abstract this proton. No, sorry. pH, CH2, H2, Cl. Now OR minus abstract this proton. Now it will become negative charge. So this negative charge comes here. This chlorine goes like this. And get this product. Now OR minus attacks to this carbon. This will become O minus OR pH. So here now the ring can open two ways. This is one way and this is another way. Imagine this is A and this is B. In the A path we will get pH, here negative charge, CO, OR, and in the B path we will get here negative charge, pH, COOR. So which is more stable here? Obviously this carbocation is more stable because it is close to the phenyl ring. So we know that close to phenyl ring that is more stable. Okay, so this will be the major product, pH, CH2, 1 2 3 4 1 2 3. So this is major because here this carbanion is stable and this carbanion is not stable. It may form, but it's forming, it will form in a minor amount. So this is the mechanism for these kinds of compounds. And now we'll go for different types of substrates. And this is also very important. CH3, CH, Cl, CO. We'll see this compound now. Here we have base. Base will obstruct this proton. Negative charge, and here chlorine will come. Now the asymptote mechanism follows. Okay. Now the ring okay, or minus comes and attached to this carbon, O minus OR Cl CH3 and methyl group. Now this bond goes like this and this bond goes here. Chlorine is a leaving group here, so finally we will get double bond here CH3. So this product we will get. So when we have a one chlorine only, that time we will get this kind of product. When we have a two chlorines or two halogens next to CO group, in that case we will get a alpha beta unsaturated esters. Whereas when we have only one leaving group, that time we will get a simple esters. When we have two leaving groups, that time we will get alpha beta unsaturated esters. And here we have a 7-member ring. I am not writing mechanism for everything here. I'm just directly writing the product. Just ring contraction takes place. So this is 7-member ring. 7-member ring converts into 6-member ring esters. Then we have same 7-member ring, but two living groups there. We know that if two living groups are there, we will get a alpha beta unsaturated esters. Here also you can practice the mechanism, whatever mechanism I have explained before. And then this kind of compound gives this as a product. Here also it's a 5-member converted into 4-member. And then now here we have two bromines at same carbon, and here also same mechanism. Here also we'll get a alpha beta unsaturated esters. Next, so this is the question they asked in a previous exam, in a CSET exam. This is A, and here we have dipole H, it's B, and we have here PH3P double bond CH COET. This is C. So we know that this is the Favorskii rearrangement. Okay, in Favorskii rearrangement what will happen? So ring contraction takes place and alpha haloketones converted into esters. And in the second step, dipole H converts esters into aldehydes. And here temperature is mentioned. This is low temperature. So dipole H at high temperature, everything gets converted into alcohols, but at low temperature esters converted into aldehydes. And next we have a Wittig reaction. So finally we will get a finally we'll get this product. This asked in an exam. And this example also very important, this one. We have bromine here, this is A, then we have OCH3 minus B, then we have only B. Okay, so here now here bromine, we know that bromine addition to double bond will be in a trans fashion, right? One bromine will be this side, another bromine will be this side, double bond. In the next step we have Favorskii rearrangement. Okay, so without writing the mechanism, I am just writing the product. So I just said that if two living groups are there, we will get alpha beta unsaturated esters, right? So now I am writing directly product, and then contraction also takes place. So here two product will get. One is cis, so another one is one is trans, this is trans, another one will be cis. Here trans is major. I did not write the mechanism here, I am directly writing the product. I have explained this mechanism before, I just practice same mechanism here also. And then here we have another example. Br in the presence of OCH3 minus, this will obstruct this proton. Negative charge, it goes like this, it came like this. Now we have a cyclopropane formed. So now this will be open. It can be open in either side because it's a symmetric. Okay, before that OR minus goes and attacks here. Now this goes here, this comes here, and here we'll get a 2 5-member ring. Just remember, when 2 5-member rings are fused, 2 3 4, so when we have a 2 6-member ring, in that case always trans product will be major. When we have a 2 5-member rings are fusing, in that case always this product is major. Just remember this point. In case of NBu3SNH, so this kind of stereochemistry will come. So I'll also make video on this NBu3SNH. So that time we'll talk about the cis and trans geometry in case of 2 5-member fused systems. And this is about the Quasi Favorskii rearrangement. So another rearrangement is called as Quasi Favorskii rearrangement. This is also very important. So in the Quasi Favorskii rearrangement, So this is the starting precursor. Okay, so now we have a OCH3 minus. So in Favorskii rearrangement, this is the last step where OCH3 goes and attacks to the this CO bond. That is the last step. First step is abstracting this hydrogen, right? But here the first step is going and attacking to this CO bond. Now this is Cl, this is O and OCH3 and pH. So now this bond goes like this, and this pH is a migrating group, and this chlorine is a leaving group. This chlorine goes here and this phenyl goes and attacks to this carbon. So we'll get here no ring contraction. Okay, so this is the final product in a quasi-Favorskii rearrangement. So first step is attacking of OCH3 minus to CO bond, and next step phenyl migration takes place, and Cl goes a leaving group. So finally we'll get this product. And here also we can explain this quasi-Favorskii. pH and chlorine, and the first step is OCH3 goes and attacks here, this chlorine, O minus OCH3 pH. Here also same, chlorine is a leaving group, and phenyl goes and attacks to this carbon, and we will end up with COOCH3 and pH. And then here we have and there is a question in a gate chemistry. This is the question asked in a gate chemistry, COOH. Okay, so they just asked whether this reaction belongs to Favorskii rearrangement or quasi-Favorskii rearrangement, then Smiles rearrangement, fourth one is neighbor rearrangement. Actually this belongs to a Favorskii rearrangement, but the answer is quasi-Favorskii rearrangement. I will explain why. So if we use Favorskii rearrangement, we will see the mechanism. So OH minus abstract this proton, now it will become O minus, CH minus, and bromine goes and it come here. Here there is a formation of this kind of system. Actually this is unstable, highly unstable, so this won't exist. So because of that reason, this further step will not go, means it cannot form by Favorskii rearrangements, because this is highly unstable and unfavorable. So this has to go by quasi-Favorskii rearrangement. So we know that what is the first step in the quasi-Favorskii rearrangement. So O minus OH Br. So this goes like this, and this is a migrating group, comes here, and we'll get this compound. So this comes under quasi-Favorskii rearrangement. So this is about the Favorskii and quasi-Favorskii rearrangement. I have some examples for quasi-Favorskii rearrangement. If you practice more examples, then it will be easy to remember.